Behind the Knife, the surgery podcast. Relevant and engaging content designed to help you dominate the day. Thank you, as always, for listening to Behind the Knife. This is Patrick Georgioff. We love our APP colleagues, and we know that you do too. But when we surveyed the barren landscape, there wasn't a single high-quality surgical education resource made just for NPs and PAs. And that's why we created Dominate Surgery for APPs. This kick-ass resource has it all, from core rotation-specific knowledge to practical tips and tricks like how to present a consult, insert a laparoscopic port, and find your first job. It contains short, high-yield text, beautiful illustrations, tons of practical audio, and professional-grade videos. Group discounts are available. Now, enjoy the episode and dominate the day.
Hey all, I'm Ayman Ali. I'm one of the Behind the Knife Fellows. Welcome back to our series on artificial intelligence in medicine, where we break down exactly what you need to know as a clinician. Today, I'm joined with a couple of guests from Oregon Health and Science University. First is Phil Jenkins. He's a general surgery resident and a National Library of Medicine postdoctoral fellow who's pursuing his master's in clinical informatics. Welcome, Phil.
Thanks for having me.
And for faculty, we're joined by Dr. Ruchi Thanawala, a thoracic surgeon with a background in AI and informatics. Dr. Thanawala, welcome back to the podcast.
Hey, Ayman. I'm very excited to be back on Behind the Knife with you, and I'm really looking forward to the conversation and discussion today.
And lastly, we are also joined by Dr. Stephen Bedrick, an associate professor of biomedical informatics and machine learning researcher.
Thanks so much for having me. It's a real pleasure to be here talking with y'all.
And it's great everyone's here. So last time on this podcast series, we talked about computer vision, how AI models interpret and analyze visual data like radiology images, operative videos, or endoscopy footage. Today, we're going to explore a different but equally transformative domain, how AI understands language. To do so, we'll talk about natural language processing, or NLP, and the rise of large language models, LLMs. Phil, what are popular examples of large language models, and why should we care?
So if you've heard of ChatGPT or DeepSeek, those are large language models, and they have taken the world by storm. They come up in many conversations, more importantly in tools that are rapidly being integrated into healthcare, from helping draft clinic notes to answering patient questions. And we think it's critical for clinicians to understand what these tools are and how they work, as well as understand their limitations as well as their potential.
Phil, you know my soapbox really well. I couldn't agree with you more. In my eyes, there hasn't been another time in surgical history where technology is actively changing our world at a rate like it currently is. And large language models are a big part of this revolution in AI in medicine. Also, what is so super interesting about LLMs is that it's being used across the board. ChatGPT, for example, has made LLMs so accessible by our patients, to individual physicians, all the way to scientific and operational groups in our healthcare systems.
Exactly. It's impacting everything today. And today we're going to try and get to learn about them. And to do so, we're going to start with natural language processing. If LLMs are like robotic surgery, NLP is kind of like laparoscopy. NLP is about trying to understand and even generate language. But to do so, we have to break language down to parts that a machine can understand and interpret, which is not quite as easy as it sounds. Dr. Bedrick, Dr. Thanawala, let's start off with some important definitions that we need to talk about first.
So the most important thing to understand about NLP, right, is that computers fundamentally work with numbers, not language. And computers are also what we would call closed and very simple systems at root. So practical level, everything about NLP is figuring out how to take something that in reality is infinitely complicated, human language, and then break it down, like you were saying, into small pieces. I think of it like a modeling exercise, much in the same way that when an epidemiologist does some sort of analysis of a disease outbreak, the way they attack it is they make a little model of different kinds of exposures and different kinds of outcomes and try to reduce the number of moving pieces to a small manageable number that they can understand, even though they know that there's in reality an infinite number of things that could be contributing to the phenomenon in question. So analyzing language in this way, it usually involves breaking it down into a few kind of basic building block pieces, and each of those pieces has an associated kind of purpose for doing it.
So Ayman and Phil, I think it's good we start with some basic definitions because I think for us to have a meaningful conversation, we should really, use some shared language. So first, I'd like to define tokenization. So this is the basis of NLP, which is breaking sentences into words or phrases. This concept will be important later when we're really starting to get into large language models. The next, part of speech tagging. So after you've broken down your input into words, then a fundamental task becomes assigning a grammatical category to each word, which helps you to really understand relationships between words and sentence structures. So finding the verbs, adjectives, nouns, and onwards. And third, disambiguation. Words have the same pronunciation or spelling. We experience that all the time, but really can mean different things. Humans are good at using context to figure this out. Ayman, can you give us a clinical example of this?
Yeah, there are infinitely many clinical examples because we use way too many abbreviations. So, for example, DRE could be a digital rectal exam, especially for surgery residents, but it could also be a dilated retina exam, or something to do with hip hop or a different group that we don't know about. And then, what is disc referred to? Could that be a cylinder or an anatomy or cartilage between vertebrae? I mean, we use lots of abbreviations and it is hard to figure this out. Dr. Bedrick?
Yeah.
Or other definitions?
Well, once we have our sort of words represented to a computer, right? Once we have our sentence taken into tokens and we've kind of figured out what words are words and separated them out, usually then we start trying to do higher level kinds of analyses of the input. So one sort of next level thing we might try and do is what's called co-reference resolution. So we might have a sentence that uses determiners like the and it and that, or other words to try to link concepts between phrases or across sentences. And when we're having humans processing language via either reading it or speaking it, we're really good at figuring out what we're talking about. Computers really struggle. So Phil, can you think of a clinical example for this one?
Sure. If you when you get sign out or you're talking about a patient, you would say something like on admission, his SpO2 was 85 on room air, but it rose to 95 on supplemental O2. So it's kind of understanding, how does the computer know that it refers to the patient's oxygen saturation, or those types of things that humans are really good at figuring out, but would require a lot of computer science to really train a model to do it well.
Exactly. But is very important for making sense of that sentence, right? Um, Another really important task for clinical applications is what's called entity recognition. So if we have a sentence that might have various actors in it or various objects being discussed, trying to figure out what those things are. For example, that if in a sentence talking about aspirin, that aspirin is a medication, or a sentence mentioning Dr. So-and-so, that Dr. So-and-so is a person. So figuring out kind of who are the moving pieces in a sentence. And then related to that is entity linking. Once we have those entities identified, frequently in medical applications, the next step is to map it to some kind of controlled vocabulary or database. So for example, knowing that the string aspirin represents a very specific medication, or that if the sentence mentions paracetamol or Tylenol, they're talking about acetaminophen, and mapping those to a controlled thing. We use a lot of vocabularies like SNOMED, and we also use things like ICD codes or other related taxonomies. And then finally, the last piece, which is not really the last piece, but it's kind of a big category of pieces, is the larger context. So it's very, very, when humans are using language, we're using language for a reason and in some kind of social or practical or organizational context. And computers by themselves don't really understand very much of that. So practically analyzing language with computers, you need to have some way to tell the computer about that larger context. Without that context, even sentences that seem very straightforward might have very different interpretations. So Phil, I think you might have had an example for this one.
Yeah, so an example would be like, does discharge refer to the salmon-colored fluid that's pouring out of the laparotomy site, or does it refer to the patient leaving the hospital?
Right. And this is the sort of thing that has really changed with LLMs. Everything I've described up to now, we certainly were doing before LLMs, and some of the things we've described, LLMs do kind of implicitly by themselves, and we don't do by ourselves anymore as computer scientists. But the context piece is something that LLMs have really changed, because it's a lot easier to have the computer know about more complicated contexts in much more clear ways than the ways we used to have to try to fit context into computers.
So ultimately, natural language processing takes a sentence and breaks it down, then tries to understand the pieces and gather context to provide an answer. As Dr. Bedrick has taught me through multiple lectures, this is the who did what to whom and where and when they do it portion of it. Some natural language processing examples that you may know are like the autocorrect function on your cell phone, or translation apps, or voice assistants like Siri and Alexa. But in medicine, natural language processing also enables us to extract information from clinical notes, summarizing long documents, and even support diagnostic reasoning.
Phil, you bring up some amazing examples of NLP that exist in our regular daily lives outside of, the hospital. Um, and I mean, these have really been part of everything we do, even before most of us knew that this was a branch of artificial intelligence. The fact that there is a whole field dedicated to creating a computable understanding of human language shows just how complicated our communication really is, and how much our human brains process to understand each other, which is super fascinating.
Yeah, it is. It really is. And I think that natural language processing is such an important foundation to have. So I'm glad that we spent a little time talking about that. Now, I think it's time to move on to some of the maybe more exciting things today, which is large language models. Phil, you want to give a simplified overview of how they work?
Yeah, absolutely. So large language models, or LLMs, are an advanced form of natural language processing that require just massive amounts of data. This is based on statistical language models, which are really any statistical model that tries to predict the probability of a sequence of words following a given pretext. Large language models are trained on billions or even trillions of words across the internet, using deep learning and layers of neural networks to learn statistical patterns. In this context, what this means is what word is most likely to come next. But this really gets at the importance of data quality that these models have to be trained on.
Yeah, exactly. And an analogy would be like a surgery resident that maybe gets a page starting with level one. If you ask anyone to finish the sentence, you're probably going to guess the next word is going to be trauma, and that's got a pretty high likelihood of being correct. And then subsequent words, maybe MVC or gunshot, and these have various likelihoods that probably correspond to how often you see those things. An LLM is essentially doing this, but instead of being trained in a residency program the way we are, it's trained on the internet.
That's exactly right. And to be more specific, large language models do this using a method that's called self-supervised learning, a very important structure called a transformer, which was a big breakthrough in AI research in 2017. We touched on this concept briefly last time in our discussion of vision models, but transformers are key because they let the model pay attention to relationships between words, not just in one sentence, but across an entire document. That's how these models understand context, nuance, and even sarcasm. Though, honestly, sarcasm is still hard for these models. Let's be honest, it's hard for human brains too. It's also why they can generate such fluent, coherent responses. Dr. Bedrick, can you briefly explain how this works?
I will try. So the transformer architecture is conceptually very, very simple. Think back to what we said earlier about tokenization. It starts where we take a sentence, we split it up into its constituent words, and in some cases, sub-word units. Longer words or rare words might get split into smaller chunks. So imagine beads on a string. We take the sentence, it's beads on a string. And then what we have is those get fed into a very, very deep set of very, very simple neural networks. And uh, imagine over each one of those tokens, a set of spiderweb connections going to every other token in the input, right? A grid of boxes going over it, each box having spider webs coming out to all of the boxes beneath it. It's like a big lattice. And so each one of those cells can see everything about the layer below it, all of those inputs, and it can kind of decide it during training. It learns how to decide which of its neighbors it needs to pay attention to. And so by stacking a lot of these on top of each other, the model is able to go from in the very bottom layer, learning sort of surface features of the words about like their part of speech, for example. And then as you go at higher and higher layers, the things that learn start to be things about syntactic structure, and then finally meaning, what the words actually mean, right? As you get deeper and deeper into the network, you might see some of those cells activating more, more highly if certain words are present in certain contexts. It's still a model of the sentence. It's not the actual understanding of the sentence the way humans would do it, but it's able to capture a lot of meaning. And what's really interesting about it is mathematically it is so simple. When we it it has it makes it up in volume. What it lacks in sophistication, it makes up in volume. So under the hood, if you were to zoom in on any one of those cells, what you would see is something that looks a lot like the logistic regression model that you learned about in biostats class. The equation is not so different, and it just has many, many, many of them. And by many, I mean, you know, billions, basically, billions of them sometimes, depending on how you want to count it. And it's a true emergent phenomenon. The other piece to it is at the top layer of the transformer, at the very end, is what we call the output layer. And in the case of a language model, that output layer's job is to do what Phil was describing, predicting the next word in the sequence. It doesn't have to be that way. You can use transformers for any kind of sequential data. And that's one of the reasons why they work well for vision. That's one of the reasons why they work well for analyzing other kinds of time series data. But they were invented for language and worked very, very well for language.
Yeah, that was
Explanation.
that was an incredible explanation. And I always find it fascinating because having tried to read that 2017 paper, The Attention is All You Need, many times, it's a beautiful paper. It really is. And the foundation of it seems so straightforward. And the question I have for you, Doc Bedrick, is, you look at something like that and do you expect to get ChatGPT? Did people expect that they would get a large language model to function the way it does?
Yes and no. So the 2017 paper you mentioned was it was called Attention is All You Need. So the structure I was describing of each individual grid square getting to have spider webs going out to every one of its neighbors below it. That's using something called the attention mechanism. Basically, that cell that gets to learn as part of a statistical learning process how to decide which cells to pay attention to. And when they made that paper, it was kind of standing on, let's see, 2017, about 5 years worth of consistent progress in NLP of applying neural networks to the problem of processing sequences of words. And what was the reason they called it attention is all you need is because they basically, the attention mechanism was invented for something else. It was for a different kind of neural network called a recurrent neural network. And it was meant to solve a problem that recurrent neural networks had, which is that they also took, a sentence broke up into tokens, beads on a string, but it had the problem that the longer your number of beads on your string, they could only pay attention so far back in the past before they lost track of what they were doing. And there were a number of ways that people tried to solve this, but the way that really finally solved it was the attention mechanism. Each step of the way got to see not only his preceding neighbor, but also got a chance to kind of cheat and look further back in time. So the real innovation of the 2017 paper was they realized that with enough data and with more layers, you actually didn't need the original part of the model that they'd sort of bolted attention onto in the first place. That's why they called it attention is all you need, because we thought we needed all this other stuff and attention. And what they showed was with enough data, you didn't. And that was a really, really big deal. And it was a bit of a surprise to all of us, I'll admit. Like, we didn't think something that simple could work. The equations, they really are surprisingly simple for it to work. It's very neat. The only reason it works is because of the vast amount of data and the vast amount of compute. The other piece to the puzzle, by the way, is because it uses such simpler math, we can get away with using more layers and more data for a given compute budget. Whereas the RNN architectures I was describing had a lot of things that made them challenging to make efficient on large amounts of data. The transformer architecture solved all of that. But even then, the attention to all you need paper, they were using it for machine translation, which does have a text generation component to it. But they were using it in what's called an encoder decoder architecture, which is probably more detail we really need to go into. The upshot is it was for one kind of task. What the next year at the big computational linguistics conference, people were using transformers for a lot of other tasks beside machine translation. And the year after that, people started using the same transformer model to do multiple things, right? So it started off just for machine translation. The next year, they were using it for a lot of different sequence processing tasks. The third year, they were using a single model that they trained to do translation and all these other tasks in one model. And around then, we started kind of wondering where's all this going to go, right? People started using it for things like document summarization. People started using it for things like powering simple chat agents. But I don't think any of us really saw ChatGPT coming. And what happened with ChatGPT was they scaled it up again. They took what people were doing, made it bigger, gave it more data, and then added one or two other ingredients that we'll talk about in a few minutes. And what they showed was a lot of these things that we thought were very different. Like if you'd asked me about like a general question answering dialogue capable algorithm that can do whatever you know, can write limericks and summarize and abstract, I would have thought those needed to be separate things. I personally was very surprised. A lot of us in the field were very surprised that it worked. We'd seen things scaling up, we'd seen the capabilities increasing, but we didn't expect it to work as well as it did then. And we also didn't expect it to take off in the kind of public imagination the way it did. That was very, very surprising. And so that was a long-winded, complicated explanation. I will also just say that, we have always in our field, the vision has always been be able to talk to the computer using natural language and have it talk back. I mean, when they first coined the term artificial intelligence, back in the 50s at the Dartmouth conference, where it was, kicked off, they talked about, not, natural language interaction as like a thing they might go for. It's always been something we wanted. But I and everyone else always sort of assumed it would need a lot more complicated software in there. And what we really needed was a fairly simple model, just made very, very, very large, and then given a lot of data.
That was a really great explanation. Just to clarify, these models, they were expected to do well with transformers, but not this well. Really taking, just protecting the next word based on probability, and really expanded and exploded into all the stuff we see today. But because they've seen so much language during their training, they've learned all these patterns with grammar, style, reasoning, and made them the tools that we see today. It's really fascinating.
So I agree. This is all great. But should we talk about a few more important points? Phil, what's fine tuning and what is hallucination?
So broadly speaking, fine tuning occurs after the initial training of a model. But at this point, the model understands language, but not how to be helpful or useful. So after teaching the model language, the next step is to train the model with data sets that have correct answers or labels, which is what we call supervised learning. This is where the model becomes able to interact and give you, hopefully what you want.
That's right, Phil. If I can expand on that for a second, that that fine tuning can take a few different forms. One form it can take is if you have a specific kind of data that you want your transformer to be more familiar with, right? So, for example, a classic example is in biomedical data, right? If you have a transformer that's trained on the general internet, but you want to use it in a medical context, a very common thing to do is then do a few more rounds of training on, say, PubMed, right? Where that will teach it more about the kinds of patterns and the kinds of language we use in medicine, and maybe help it learn a few things along the way, some more information. Another way that the fine tuning can happen for a large language model is through something called reinforcement learning with human feedback, which is more like what Phil was mentioning, where you have examples of positive and negative outputs, perhaps to the same question. And humans give the language model signals about which answer they liked more, and they might be focusing on things like which answer was more closely following the instructions it was given, or which answer was less racist, or which answer was more factually correct. And with enough of those, that can help nudge the model in certain directions as well. And that happens after the large pre-training process. And the third kind of fine-tuning that can happen to be very, very task specific. If you know that your model is only going to be used for example, predicting whether something is spam or not, or triaging in-basket replies, for example, you might have a set of very, very carefully labeled data, and you are going to be doing a set of additional training where you're not even necessarily trying to get the model to generate language. What you're instead doing is asking it to make, say, a multiple choice prediction about how to handle a certain input. And in that case, you maybe don't want it to generate a lot of extraneous commentary. You just want it to say this is about prescription refills or scheduling an appointment or something else. And that sort of fine tuning takes a different pattern. But in all the cases, the sort of overall shape is that you have a fairly clear notion of what it is you want the model to do, and then you put it through a very specific training regimen from there. And then Dr. Thanawala also asked about hallucination, which is a very, very, very important concept with large language models. So large language models, it's important to understand, don't actually know anything. They are just statistical models, like a giant overgrown linear regression model of the data they were trained on. And so what that means is their output can have errors. Sometimes those errors are, because the information that it needed wasn't that it needs to answer your question isn't something it saw during training, so it's not something it has access to. Other times the errors are because of a statistical noise. Sort of loosely, all these errors get lumped under the category of hallucination, meaning outputs that are not real. There can be hallucinations of fact where it makes a factual error. There can be hallucinations of fidelity where it ignores your instructions. Perhaps you tell it, not to mention the pink elephant, and it mentions the pink elephant, for example. Or it can misunderstand something about the input. These hallucinations have the unfortunate property that they all are very statistically plausible looking. So the thing the language model is fundamentally trying to do from its perspective, it is trying to make an answer that looks statistically like what it saw during training. And, if you imagine the sentence, the patient has a, blood pressure of 70 versus the patient has a blood pressure of 75, those are both perfectly plausible answers. One of them is accurate, right, for your patient. But from the model's perspective, in terms of how likely are those numbers to occur that are about in the same ballpark range, right, the model is going to potentially make those errors. So it's very important when you are using large language models to know that this is a thing that can happen, and know to look for it, right? Models can make mistakes. They do make mistakes. It's kind of baked into how they work. And I was going to add one other thing. That's an important difference between a large language model and something like a traditional database. So a traditional database, if you run a database query to see if there's any patients over a certain age in your clinic, like Epic is not going to make up a patient that's not there, right? It knows for sure what patients are there. It knows how old they are. It will show you exactly the right ones. That's not really how LLMs work. And they will give you an answer. And that answer might be right, or it might be one that the model thinks is a likely answer. It doesn't really have any notion of right or wrong or true or false or reality or not reality. That's not really the kind of model it is.
Yeah, I think hallucination is something that's actually very straightforward to understand in medicine because we see it every day. And medicine is, the reason that we have so many checks in medicine and the Swiss cheese model and all of that, the reason we have that is because of, honestly, a hallucination that we do. We might look at a patient's hemoglobin in the morning, not actually look at it, but say it's unchanged from the day before. And statistically, you're probably right most of the time, except for that one time that you're not. And it's very hard to catch that unless somebody else goes in there that's trained, knows what to look for, and checks exactly that value. So I think clinically we see hallucination all the time in the hospital, which is why we have the systems that we have.
Like
Yeah.
that's a really good point, and this is another important thing to know about LLMs. So we have the systems we have in hospitals to prevent those kinds of errors because we have a good understanding as humans of the kinds of mistakes we're likely to make, right? You're not likely, you're likely to maybe to miss a hemoglobin measurement or to get two patients mixed up, but it'd be very strange if you made up a whole new thing, right? That's usually like a very anomalous kind of error. And when that happens, that's actually usually very hard to catch, right? Sometimes, whereas like the small little slips are easy, and so we have a lot of processes in place to try to catch those because we have a good mental model of what those errors are. LLMs, we don't have a good mental model for the kinds of errors they're likely to make. Sometimes the errors they make are very different ones from what humans would make. And so it's hard to reason about what they are or aren't going to do, which is a real safety consideration when using them, and is a reason to be very careful.
Yeah, definitely. I mean, it makes a lot of sense sometimes for humans to check other humans, but LLMs checking other LLMs gets very complicated. And
Right.
so I think those are really, really important points. And the other small point I wanted to make, which is just a small one, is that I saw that there were some papers coming out that show that some of these very fine-tuned models, like your bio, ChatGPT, etc., don't actually perform that much better. And of course, part of that is because it's very difficult to measure performance of an LLM. And I just wanted to hear your thoughts about that briefly, because there is a lot of hype about these very specifically fine-tuned models. But some of the literature I was reading was not quite as convincing.
Yes, that evaluation is one of the biggest challenges. So some kinds of learning models, we have good understanding of how to evaluate. So like a sepsis prediction model, right? We know how to evaluate a sepsis prediction model. There's a clear, discrete outcome. We know who gets sepsis. We know who doesn't. We can calculate metrics like sensitivity and specificity and all of the ones that we're used to. Something like a large language model, if we're using it as part of a decision-making process that has that kind of outcome to it, then we can use a similar evaluation strategy. But when we're using it for things like helping draft a note or doing, taking a first stab at responding to a patient's query or answering a clinical question like what's my risk of a side effect on this medication, that becomes a much more challenging evaluation problem. And uh, one way to think about this is any kind of measurement, right? We go back to measurement theory. We have constructs, right, which are latent, unobservable phenomena, and then we try to operationalize those in something that we can measure, and then we try to accurately measure those, and then we hopefully have things that we measure that have good external validity, right? When we think about LLMs, we use them for so many different things. There's so many different latent constructs that we want them to be able to do. So evaluating them, it's very hard to have a single benchmark number that's going to be good. If you look at how LLMs are ranked, they're frequently using ensembles of lots of different metrics and different measures that are trying to get at different kinds of phenomena. Um, it's unfortunate, but if you scratch the surface of many of them, you'll find that they have frequently very low construct validity, or very questionable construct validity is another way to put it. Um, you know, you'll see something that talks about measuring, hallucination level, and you'll see that the way they operationalize that is very flaky or is very, very specific to one kind of hallucination. And so evaluation is very, very difficult, I guess is what I'm saying. And it's very hard to say that one model is better than another in some kind of general way. Now, to your more specific point about the clinical, like domain specific models, the way people try to evaluate those is first they try to show that the fine tuning or the additional training on clinical domain knowledge didn't impair its performance beforehand. There's something in machine learning called catastrophic forgetting, which can happen when you take a model trained to do one thing and then do more training on something else. And if you're not careful, it'll forget how to do the first thing. So the first thing they try and do is make sure that there hasn't been catastrophic forgetting. And then usually they'll have some clinically relevant measures that they care about. They might use a benchmark data set of question answering performance, like biomedical question answering performance. So they might have a benchmark data set, something about, like USMLE test scores or something, right? And they will hopefully try and show that, yes, training this thing on PubMed a bunch of times, now its performance on the biomedical question answering task went up 3 points. Right? Sometimes it does, sometimes it doesn't. Sometimes it goes up, but other things go down. I think, the latest models that I've seen that are fine-tuned for biomedically specific tasks, generally are a little bit better at some of those measures. Anecdotally, I'll say that if you ask them to generate text, one thing they do better at is they do better at producing text that kind of follows the linguistic patterns and norms of, say, medical notes or biomedical abstract or something like that. That's a little bit vaguer and hard to kind of quantify. And so figuring out how to evaluate all of this is very hard. People try and make it as concrete and task specific as possible. But when you're choosing one for your purpose, you want to make sure that whatever measures they were using are ones that are actually relevant to what you care about.
So we touched a bit now on hallucinations and challenges for the evaluation, but Dr. Thanawala, what are some other hesitations that you have for using LLMs in the clinical environment?
So, as you mentioned, we've already talked about hallucinations, and that's a big one. In medicine, incorrect information can be harmful and really lead to injury or worse. Also, using LLMs can introduce biases in patient care. The harmful part and the biases are not apparent to physicians and patients, and that is actually compounded on biases that already exist in our healthcare world. Patient privacy and HIPAA is also really important, and solutions have to really abide by these laws, which can be difficult practically. To that point, AI and ML based software requires FDA approval. And that just really shows how we really need to identify and define the safety of tools like the ones we're talking about.
Yeah, and the other point too is LLMs are trained on the internet, and the internet has biases. It's stuff that we have put up there, and this perpetuates into the model as well, and that's a really important consideration to keep in mind. Also, the very small detail, there is a cost of running the model, and it's maybe not as small as I just said.
That is a good point. I mean, the cost in environmental terms is also not zero. So that's another important thing to keep in mind. I just wanted to elaborate on the bias piece a tiny little bit. Um, you know, the you might wonder why it is that models, would have these biases, right? If they're the thing about LLMs, right, is they're trying to replicate what they've seen. And so if they've seen things that have biased language, their output will have biases, and the kinds of relationships that they learned will have biases. So like a good example that I use with my students, there's a wonderful blog post called How to Make a Racist AI Without Even Trying. And what you do is you take a data set of restaurant reviews and you train a neural network to predict positive versus negative reviews, right? Um, and if you start by if you take a neural network that's trained on like regular text and then fine tune it on the restaurant review problem, what you'll find is if you take your restaurants and swap out an Italian restaurant for an Ethiopian restaurant or a Mexican restaurant, for example, pretty reliably, the same description of the restaurant will get a lower predicted score for some of those categories. And it's because the model learned negative associations with some of those categories. That's called a demographic perturbation study, and is one of the ways we assess bias. Now, people have tried this with medical text and medical problems as well. And there was a really wonderful paper that trained a network on a large data set of EHR notes and trained it to predict diagnosis codes. And what they found was that the same case presentation, if you changed from a white male to a black male, suddenly the likelihood of drug disorder related ICD codes went through the roof. And that's not really good. We don't want our models to do that kind of thing. That's not what we want them to do. And what this illustrates is yet another illustration of the models not actually understanding the data that they're shown in the way that we understand the data. Models are very, very good at learning correlations. And in this particular case, the authors figured out it was because the data in the hospital the data set came from, because of the demographics of the neighborhood, there were more Black patients that had drug disorder diagnosis codes in the data set, but obviously there's no clinical causal reason for that. That's a demographic quirk, right? So the model learned that correlation, but then went and perpetuated it, right, on new data, because it didn't quote unquote understand that was not something inherent to those patients. That was uh, uh, that was a correlation that it learned. So think about correlation and causation. LLMs know all about correlation. They know nothing about causation. So that's another thing to keep in mind when we use them. But it's tricky because the way we interact with them is with language, and we're used to imparting intention and causal understanding on things that we interact with language. We're used to anthropomorphizing, and that's a real issue with using LLMs in clinical contexts.
Yeah, I think that looking at LLMs and they're trained on the internet, so they can really be like sometimes the most unflattering reflections of ourselves and our society because their data is trained on what we've trained them on. So they're really learning from us. So if we don't like the biased output, we should kind of look at the data that they were trained on. And there's a lot of hype around LLMs. I mean, I think and the potential is very real. And I think that this conversation is really important that we learn how to integrate these tools responsibly and critically think about their abilities, continue to validate them, understand what happens when they fail, and ensuring that they support but not replace clinical reasoning.
Yeah, and this episode has been fantastic, and I've learned a lot too. And I think that as we start to wrap up, we should talk about a couple of real life examples, and also a good time for Dr. Bedrick to highlight some of his research. And so just to start, a couple of real world examples. So there are a couple of tools out there now which are working to summarize patient histories with large language models. I think this is a really fantastic use case of large language models. It really is where they shine. The risk becomes much smaller, I think, when you're summarizing material as opposed to trying to generate some new ones. So it is a fantastic use case, and it's really good at taking language that clinicians sometimes we think is reasonable, but is really not easy to read, and breaking it down into a form that a patient at any level of understanding can get out. Now, the other tools that are out there, there are a lot which are probably coming to your institutions about helping write clinical documentation. I think it's a little early to know how they're doing. Mixed reviews, and obviously they work really well in some settings and not as well in others. Classically, a good example is they're going to be really good in outpatient, where you're sitting and having really intentional conversations with patients, and probably a little bit less good in the emergency department with the surgery resident trying to reduce a hernia. It's probably not going to do quite as well at generating a note there. Uh, the other thing is there are a lot of research groups that are using large language models and really leveraging them to answer complex medical questions. And I do want to point out that the transformer architecture we talked about before is very useful in some time series work as well, which is some of the research that I'm doing as well. Dr. Bedrick, any good examples from stuff that you're working on right now?
So, one way that we are using them is we have an NIH-funded project that looks at cohort discovery, so identifying subpopulations within an EHR database that match certain clinical criteria, for example, trial eligibility or as participants in some other kind of study. And this frequently involves using both the structured and unstructured part of EHR notes, and so we're using LLMs to help implement that. And what's really interesting about that one is we're doing it across multiple sites and studying ways that we can, we can't share our data, but maybe we can share some of our algorithms and models across sites and leverage, multiple sources of information that way. And then we have another project going that is looking at, summarization of EHR notes for for two kind of main use cases. One in care management, so the inpatient to outpatient handoff, when you might have a patient who was hospitalized and had a lot of different things happen to them, and now their cardiologist maybe doesn't need to read about their whole week-long stay in the hospital. They need to know about what happened specifically related to their heart condition, right? Or maybe like an adverse event or something that had them referred to the cardiologist. Um, so kind of focused, tailored summaries. And then we're also doing similar things to help patients understand their notes. And then the last one is that I have a whole other line of research on speech and language disorders. And so we're using LLMs to help with automating different kinds of assessments for post-stroke aphasia in patients. So that one's working with speech and language pathologists and is a totally different use of LLMs, but is a very interesting one.
Those are all amazing applications, and honestly, I cannot wait to see what LLMs do to our clinical environment in the next couple of years, because they will change a lot. And Dr. Thanawala, Dr. Bedrick, Phil, any final thoughts to wrap this up?
I think that I know personally I've learned a lot in the course of this conversation. So I can't thank you all enough for taking on the topic of large language models and natural language processing in healthcare. I think at the end of this and in general, we just realize how much there is to really learn and know about these technologies to safely apply them. And the more we know about them, the better we'll be able to take them to our world and do good with them.
I'll just say thank you so much for the opportunity to be on here and talk with you all.
Thank you all, and from behind the knife, dominate the day.
Dominate the day.
Be sure to check out our website at www.behindtheknife.org. Download our free app available for Apple, iOS, and Android. Simply search for Behind the Knife in the App Store or Google Play to download the app. In the app, you can listen to our episodes, watch high-yield videos, and even access our premium content, including our oral board reviews and trauma video atlas. You can also follow us on Twitter at Behind the Knife and on Instagram at Behind the Knife Podcast. If you like what you hear, please be sure to leave us a review. Content produced by Behind the Knife is intended for health professionals and is for educational purposes only. We do not diagnose, treat, or offer patient-specific advice. Thank you for listening. We appreciate your support.
Until next time, dominate the day.